know that, right? What's the area of a rectangle? Length times width. Good. So I can start with that, right? Area equals length times width. But when I'm going to be honest, every problem you do in this section, you can put this in your notes. Different from related rates and optimization. Make sure your function is in terms of one variable. You need that at the beginning. Before you differentiate anything. Before you differentiate anything, and differentiate that function, make sure it's all in terms of one variable. That means one letter. Your function that you're trying to maximize or minimize. Will you remember that? So put that in your notes. If you want to go, all right, in optimization, no matter what, I'm going to get my function. I'm going to maximize it or minimize it, but I'm going to make sure it's in terms of how many variables?
One.
One before you start. Well, I love that you all just told me LW, but I'm not going to differentiate yet. No, because I want it all in terms of one letter. Now, and because this is the x-axis, and this is the y-axis, and that point right there, that's a point on the curve. Isn't that the point x comma y? So in this image, check this out. Can I call that distance y? Let's do it. And from here to here would be the distance y. Okay, that side's y. And I want to be careful because this is the origin. So what's the distance from here to there? That's distance what?
X.
X. So help me out. What can I call the length here? Not just x. How many x's?
2x.
2x. Now some people get confused because they go, doesn't it go negative over there? But distance is positive, right? So if this is length x, we can definitely call this whole length right here 2x. So I'm going to call length 2x. Now, I'm still in a jam. Because before I do a derivative, before I differentiate this function, I said I have to have how many variables?
1.
I'm still got the sad face. Someone's going to help me out. So this is where you look with your eyes. You're going to take your time. You're going to go, okay, I know there's a way I can write this whole thing in terms of one variable. And you're going to look back to see if you can substitute something. Take your time. Look, I'm at it. This is great. This is nice. I love it. 2x times y. I need it all in one variable. It's like I want all x's. Can I substitute some for that? And you look back at your image. And you look back at this. And you see something.
9 minus x
Well, are x and y equal or?
Oh, x and y are not equal.
Okay.
It could be. There'd be a nice square in there, but if they're not equal, they don't have to be.
Do you
Something else though. Do you see something?
Yeah, 9 minus x squared.
You got it. It's almost like, say, I'm going to just open up my eyes and I'm going to look around. There's going to be something where y is in terms of what? X. This goes for every problem in this section. You just get your eye and go, where is it? I wrote it down somewhere. I got to find something where y is in terms of x. And Josephine, we're like, what can I substitute for this y now? That 9 minus x squared. So I'm going to take this, here it is. Oh yeah, I can put that there. So area equals 2x times what now? Now, don't you agree? If I'm about to differentiate this thing, I don't want to do product rule. Can we distribute? Thanks. I don't want to do product rule. Let's distribute that. What would that be?
18x minus 2x cubed.
Oh, bam! Now the fun starts. I think you're going to find this easy.
You can pull out in that.
Yeah, but leave it like that. Leave it expanded. Here's my reason why, Amber. We're about to differentiate. Can't we just do power rule in that? Power rule in that is going to be easy. We wouldn't want to do product rule or anything.
Wouldn't you just do the product rule? Or, oh no, not the, okay. Yeah.
That's what I'm thinking. Now, Ellen, here's what's going on. What's the theme of optimization? We just did this in 4.1 and 4.3. How do you match? That's a function, right? Oh, it's a cubic. Oh, but it's a negative cubic. Okay, this graph maybe goes like this, right? Does something like this, and this is called a local what?
Local max.
How do we find max and mins in this class? There's something we set to 0.
The first
We
derivative.
take the first derivative, and we set it equal to what?
0.
So every problem in this section, once you got your fancy nice function in terms of one variable, you're going to get the first derivative, and then you're going to set it equal to what?
0.
And then you're going to solve for x. Now if you get one answer, that's going to be the answer, I bet. But if you get more than one answer, we can play around with it. Well, let's see. Ready? A prime? Unless you want to write dA dx. What's that derivative?
18
What's
minus
that derivative?
6.
6x.
Sometimes I get that on the test. What's wrong? Yeah, power rule, right? 6x squared. Now, can you solve that?
Yeah.
Because you're setting this equal to what?
0.
Notice, oh, here's another error. Kelly, people said 18x minus 2x cubed is 0. No. What do we set to 0? The derivative of the, yep, the derivative of that function. Just like this. F prime equals 0. So now, I'm thinking like before, I don't want to do quadratic form, Belraz, right? So I'm
Yeah.
like, how about I subtract 18?
Mm-hmm.
And so you get negative 6x squared equals negative 18. Multiply a negative on both sides, I get 6x squared equals 18. Divide the 6, I get what? Ooh, so I'm getting two answers. We'll talk about this. Plus or minus 3 or plus or minus the square root?
Root. Square root.
Alright. Now, which one of these can I trash? Because this has to be positive length.
The negative 3.
Yeah. So the dimensions find the dimensions of this rectangle, I'm just gonna give a positive value. They're the same numbers, one's positive, one negative, ignore that negative. X is what? Now here's the worst thing, you don't wanna do this on the test. Is people do this. I think all this great work. I'm like, wow. They got a nice picture and stuff. And they stop here. And they leave it. And they never answered the what? Dimensions means give me this entire length and give me this entire width. Well, you'll notice something. That only represents which side? So let's go back to our image so we actually write down dimensions. That means this side right here, from here to here, is the length of square root of 3, right?
Mm-hmm.
So what's this entire side?
2.
Two of those.
2
2 square root of 3. Very good. So when dimensions are, here come the dimensions. 2 square root of 3. Now I don't know if you know about this in rectangles, you can just put by, 2 square root of 3 by, right? And then you gotta put the width. Well, what's that letter?
What?
So how do I get that? I heard it. You said take this number, what is it? Square root of 3? Austin, we'll plug it into the, oh, there it is. So can you do this? What is 9, be careful, minus square root of 3 squared? It's 9 minus square root of 3 squared. What's 9 minus 3?
6.
You got it. Everyone okay with that one? Let's do number 14. It's on page 332. So we have to know, Jess, you asked about this, I remember for the last test. What formulas do I have to know? Make sure we know area of a rectangle. Make sure we know area of a circle, what's that, pi r?
Square.
Pi squared? Make sure we know volume of a box. What's volume of a box? Length times width times
Height.
height. It's called a rectangular prism or rectangular solid, length times width times height. So listen to this,
You
this is
only
number
need to know
14.
those 3 formulas for the test?
Yeah. Cool. Remember how if it was a cone, I would give it to you? All right, I want. You want the page? 322. A box with a square base and an open top must have a volume of 32,000 cubic centimeters. Oh man, that's pretty good, but I think before I do that, I want to do 12. I didn't even see this, I apologize, Owen. Before I do 14, I like to do 12. I I know that was a box, but this is a box as well. This is on the same page. Now let's do number 12. Because before I get to the box, let's do something. They got a flat piece. It's a flat piece of cardboard. And it's 3 feet wide. So would you draw that, everyone? It's a flat piece of cardboard and they said it's a square. Let's draw that. We gotta optimize something. Right now they said when you got a flat piece of cardboard and the sides of this are what? 3 by 3 by 3 by 3. The wording by author. You're going to construct a box from this, everyone. You're going to construct a box with an open top from a square piece of cardboard 3 feet wide. All right, right now this is just flat. You agree?
Mm-hmm.
But you and I are going to construct, I'll just draw an arrow, we're going to construct a box from this thing. How are you going to do this? Just some scissors, cardboard, maybe a knife, cut out some corners and stuff. What did they say? All right, by cutting out a square from each of the 4 corners. We're going to cut out squares, and then we're going to turn up the sides. So, but they don't tell us how far to cut it. That's what we're going to figure out. That's what we're going to optimize. We're going to try to get the most volume out of the box. So I'm just going to corners, make little squares. All right, and we're going to cut these things out. How far though? That's up to us. So to start this math problem, everyone, we don't know what it's going to be yet. We got to call it a variable. Is that okay with X?
Mm-hmm.
Is that okay? All right, I'm going to call this little light right there X. That means that's X. So that's X. That's X. That's X. That's X. That's X. That's X. Right? So if you can see, like up here, that's X. That's X. That's X. That's X. That's X. That's we get it. Now, what do we got to do with this? Everyone, we're going to take out scissors, cut these out. They'll be gone. Then we're going to turn up these sides like this. Fold it up, and you're going to get a box that looks like this. That's just going to be, you're going to form this thing. It's going to be a box. It's going to have an open top, no top. Can everyone see that? If not, I'll do it with a piece of paper. It may look sloppy, but I think it'll be good enough. All I do is cut out 4 corners of the paper and then just turn up the what? The little sides. But I think you all can actually see this. When I'm cutting that out, and I'm going to take this part and fold it up like that, right?
Mm-hmm.
Cut these 2 out. I'm going to take this part right here, this little flap that's left over, and just what? Fold it up. I'll cut these out, take this part and what? Fold it up. Cut these out, fold that up. Does someone see that? It'll be something like this. But I want you to help me out. Who can tell me what the height would be when I do that? Oh gosh, good eyes. I want to make sure everyone sees that. They're saying your height now will be X. Because when you fold it up, it'll be that distance X. But this won't be 3 anymore. This is no more 3. You got to come up with something for this baseline.
3 minus 2.
I heard it. You said 3 minus 2 X's?
Mm-hmm.
In fact, that side would be 3 minus 2 X's. Let me write that. I want to make sure everyone sees that. So this would be 3 minus 2 X's. And then this side over here one would be 3 minus 2 X's. Does everyone see that? Up because that side, once we cut, I'm going to cut them out. And then you folded this up. Well, that was 3 from here to here. But what's the distance of this now? It shrunk. It was 3 minus how many?
2.
There you go. So everyone, what's the question? Find the dimensions of this box that gives the most volume. So obviously we've got to solve for X, right? So in the last problem I started with area. What problem am I starting with now? What formula?
And
Volume. Let me get it up here. Now, I said before you start differentiating, you got to get how many variables?
1.
1. Well, what's the length of that box?
3
3 minus 2x. What's the width? 3 minus 2x. What's the height? Oh, yeah. I'm smiling now. And when the rest of this problem is piece of cake. Who's really nifty with the calculators? We'll do the calculus, but I want to point something out. if you're really nifty with your calculators, I wanna point out, you can figure out, I mean, at this point, this is why I got a smiley face. Couldn't I just graph this function and see where it got to its what? Max location? Aren't there max buttons on that calculator? I mean, that's my point. The rest of this is gonna be a piece of cake for us. Because I'm so confident, even if I mess up my calculus, I can check the actual function. That was the hard part. That was the hardest part to this problem, that's the hardest part to optimization. Is you creating something out of the word problem with some function just that has only one variable. And there it is. Now, I'm gonna do the calculus, we're gonna differentiate. There's only one thing, I don't like doing product rule, so can we expand that? So start here, I'm gonna FOIL all this first. Did you FOIL all that? I get 9 minus 12x's plus 4x squared. But what's still out here? So would you expand that? 9x minus 4x cubed. So far so good? Maybe I should write this from highest power to lowest power. Some of you have that habit, that's pretty good. 4x cubed minus what? 12x squared plus? Now, common error. For test 3, common error for the final exam. Student does all this beautiful work, all this great stuff, and they set that equal to 0. Is that what I did?
No.
No, don't do that. Is this what you set equal to 0? You go, I did all this work though, don't I? No, I have to take the what? I'm trying to maximize the volume. B prime, which is what? Alright. I've got a couple options here. I could factor maybe. If I can't factor, I'll use quadratic formula, or I'll use my graphing solver to solve this thing, right? Josephine, I know you're really good at this.